Okay, in the past few videos now, we have been taking some time out to work with the binomial expansion theorem, where the exponent that we are dealing with is a positive number. In future videos, we'll learn how to handle this kind of a situation when the exponent is a negative number. And the reason why we're taking the time to do this is that this background information becomes useful when we want to deal with generating functions, ordinary generating functions, and we'll also get into exponential generating functions. And those two are very powerful tools that we can use to solve some of the more complicated combination and permutation problems. But for this video and the next video, we're going to be discussing the binomial theorem when we have it raised to a positive exponent. And for this video, we're going to solve one more simple problem, and then we want to show the relationship of the binomial theorem to Pascal's triangle. And then in the next video, we're not going to prove why this is true, but we'll try to give it some insights as to why we have this kind of relationship. Okay, but for this video, let's consider this kind of a problem. Suppose we had 4x minus y squared raised to the 9th power. So this is going to give us then a whole bunch of terms here. Suppose that we want to know this question. What is the, say, the 7th term? If we were to multiply this out 9 times. Well, we don't have to do that, of course. We just look at the formula here. Notice now that when we start multiplying, if you will, well, instead of multiplying it out, if we use our formula here, k starts out at 0. So for the 7th term, k will have a value of 1. And obviously n is equal to 9. 4x, that corresponds to the a term, minus y squared, that corresponds to the b term. So if we were to multiply this out 9 times, what would be the 7th term? Well, we look here, okay, n is equal to 9. For the 7th term, k equals 6, so there's our binomial coefficient. A, that's 4x. And what power would that be raised to? 9 minus 6, that's 3. And the b term, minus y squared, that is raised to the 6th power. So there, that would be our 7th term. If we were to multiply this out 9 times, this would be the 7th term in the series. And let's see. This would be 64 times x cubed. This would be y to the 12th. And for here, we're going to have, this is 9 factorial over 6 factorial times 3 factorial. So that would be 9 times 8 times 7 times 6 factorial divided by 6 factorial. And 3 factorial, that's 3 times 2. Make that a 4. These cancel. That's 3. So here we have 28 times 3. That would be 84. So we have 84 times 64 x cubed y to the 12th. That would be the 7th term in the series. Try to keep things in focus here as we move along. And 84 times 64 with a calculator, that's 5,376. So there it is. if this is raised to the 9th power with no problem at all, we can readily determine this right here would be the 7th term in that series. Okay, that's all we wanted to say about that problem. Again, we just wanted to demonstrate how elegant it can be to use the binomial expansion theorem. One other thing we want to comment on before we close the video out is the relationship of these binomial coefficients to the Pascal's triangle. And that is what we have here. So what we do is you start off with 1, and then you write it again left and right. That would be the second row in the triangle. And then for the third row, the first and the last numbers are always 1, and then with these here that are in between, you add them together to get the number that's in between these two 1s. That's 1, 2, 1. Then, for the next row, again, you start with 1, you end with 1. Now add these two together. That generates a 3. That generates a 3. And we have 1. Let's continue on, and then we'll show how this is useful when we want to multiply something out. Again, for the next row, it starts with 1. It ends with 1. Add these two numbers together. It gives us 4. Add these two numbers together. It gives us 6. Add these two numbers together. It gives us 4. So there is the 4th row. The 5th row, again, you start with 1. You end with 1. Now add these two together to get 5. Add these two together to get 10. Again, you get 10. Add these two together, you get 5, and it ends with 1. And just to finish it off here, again, for the 6th row, it starts with 1. It ends with 1. Add these two together, you have 6. Add these two together, 15. Add these two together to get 20. This gives us 15. This gives us 6. And this gives us 1. So, what this means is that, for example, suppose we had x plus y to the 5th power. Then here these would be our coefficients that we would have in that series there. X plus y to the 5th, that's here. The first term is going to be x to the 5th. The last term is going to be y to the 5th. And then for the intermediate terms here, the exponent on the x term decreases by 1 throughout. The exponent on the y term increases by 1 as we go throughout the series. And then these coefficients here, 1, 5, 10, 10, 5, 1, those are the numbers that come from Pascal's triangle. Here we are raising it to the 5th power, so here that would be the 5th row of the Pascal's triangle. 1, 5, 10, 10, 5, 1. So you can see how you can use as a very handy tool that if you want to multiply two numbers together and raise it to an exponent, you don't have to go through this whole rigmarole as we've been doing here in the past videos. You can use the Pascal's triangle as a very effective tool. And one other item of note regarding the Pascal's triangle, if instead of writing this out in triangle form, if we just take these numbers here and just form a straight vertical line and write them like this, these are all the numbers from the Pascal's triangle. We just didn't write it in triangle form. Now, if you look at it and we add up the diagonals here, 1 plus 2 is 3. 1, 3, 1 is 5. 1, 4, 3, that adds up to 8. 1, 5, 6, 1 adds up to 13, and you keep doing it like that. You see it produces these numbers: 3, 5, 8, 13, 21, 34, and you can see that these numbers here, how do we get 8? By adding these two together. How do we get 13? By adding these two together. How do we get 21? By adding these two numbers together. So that from the Pascal's triangle, we also generate the Fibonacci sequence. We're not going to use this in any of our future videos for solving combinations or permutations, but again, we show it to you because it is interesting in mathematics how when you're studying one kind of a problem, all of a sudden another type of problem sort of emerges from it. Anyway, okay, that's it for this video. What we're going to do in the next video is we're going to take a look at the binomial expansion theorem when this is a positive number, and we're not going to prove why this is true, but we will try to provide some insights as to why the binomial theorem works the way that it does. So come back and join us for that video, and then after that we'll try and solve some more problems.